Hi everyone. Today I'll be presenting my work on approximating global MPC for contact-rich manipulation using local feedback. This work was done under the advising of Dr. Michael Posa, and my collaborators are Vivit Bianchini and Al Ivan. Well, we see as humans that we're capable of doing very sophisticated motions with our hands and manipulating objects and just interacting with the world around us very comfortably without actually having to grasp the objects around us. And so if we want our robots to be able to do these kind of things, we need controllers that can reason about these contact interactions in an efficient manner. So let's try and understand why reasoning about these contact interactions is such a difficult problem. Let's look at this one-dimensional problem where we have this finger that can apply a force on this mass, and this mass can only slide to the right. If we were to analyze the dynamics of this system, then we can see that up until the object is actually touched by the finger or a contact event happens, the object doesn't actually move in any way. But at the point of contact, the dynamics start to change, and we have acceleration in this in the direction in which the force is applied. To be able to control a system like this, a common control method is to linearize the system about some operating point. And let's see what that would look like for a system like this, which includes contact. Let's say we were to linearize the system about this contact, about this point in the dynamics. At this linearization, we basically lost all information about what happens when the system is in contact, and essentially the dynamics just become flat and the object doesn't move at all. Let's say instead we were to pick this as an operating point around which we want to linearize the system. Here we've lost all information about what happens before the contact. And so clearly, just linearization isn't a very good way to control a system like this. Furthermore, if we were to allow this system, for example, this object to, instead of move just towards the right, also be able to move towards the left, or potentially allow it to topple over its corners, or maybe even allow the finger to slide over the surface of the object. Then, even at the point of contact, the dynamics could evolve in multiple different ways, depending on the type of contact that actually occurs. Controlling this kind of system is generally posed as an optimal control problem, where given the starting state of the system and a goal state, we can pose this as this optimization problem that is subject to the nonlinear dynamics of the system and the nonlinear contact dynamics. Some existing methods that actually try to solve this problem include trajectory optimization on a predefined mode sequence. And so let me try and explain to you what a predefined mode sequence really means here. When we talk about the mode sequence here, what we're saying is that we're defining exactly what kind of contact is happening after in the sequence of the trajectory, but not exactly when that's happening. And we sort of bake that into this optimization. And doing something like this works for like bipedal locomotion, where you have this sort of fixed gait, or where you have this like right, left mode of contact. But for the kind of problems that we are trying to solve here, which is manipulation problem, this doesn't necessarily work because we don't have a fixed set of sequence of contact mode interactions that we plan to make with any object. For example, the way I manipulate this object now can differ with every interaction that I'm trying to make with it. Additionally, the number of points of contact that actually occur when we're trying to manipulate something is a lot more than in the case of a bipedal robot, for example, where we can have multiple points at which we actually touch the object. And so we need to be able to describe the permutations of all of these possible contact mode sequences. And that makes this problem, this trajectory optimization over this predefined mode sequence, not a very suitable way to deal with this, manipulation problems. Another existing method that is done is where we do this in a contact implicit manner, where we do contact implicit trajectory optimization. Essentially, what this does is it bakes in the nonlinear dynamics associated with contact itself as part of the optimization constraints. But this kind of way of trying to solve it actually requires offline computation because of how complex this nonlinear structure of the dynamics. Other existing methods are data-driven methods, but all of these clearly require data and require training. And so we want a controller that's able to do all of perform manipulation in a fast way, without predefined mode schedules, without offline computation, and without a data requirement. And we know of another controller that actually came out of the same lab that I'm working, and it's called C3, and it's able to do all of these things. Let's take a look at how it does. We saw that optimization problem earlier, and to make the optimization more tractable in this contact implicit manner without a predefined mode schedule, what it does is it poses the optimization problem with linearized constraints. And so we see the dynamics linearized here. And we see the contact dynamics linearized. But it still embeds the nonlinearity associated with making and breaking of contact in this perpendicular side that we see here. That's a complementarity constraint. And that embeds this highly nonlinear contact interaction. And so this is how this linearization differs from the linearization that we saw earlier, where it actually is able to, it linearizes each piece of the nonlinear dynamics, but still maintains information about neighboring nodes. If that was more complicated than we would like, we can actually draw very clear physical intuition for this, where given an object and an end effector, the way this linearization would work is that it linearizes the geometry of the object about the points of contact, essentially drawing a tangent plane at each possible point of contact, and approximates the object's geometry as this sort of infinite wedge, and then tries to solve the problem. Let's look at what the limitations are. So what just happened here? In the previous video, we saw it consistently able to roll the ball in a circle. But right here, we see that it's kind of stuck. What we see essentially is that LCS captures the nonlinearity due to contact, but C3 is limited by the local nature of this linearization. Let's try and understand what that means. Essentially, when the end effector is in a position where it can easily make progress towards the goal, or where this infinite wedge approximation can actually help or aid motion towards the goal, C3 is able to do perfectly fine. But what if once the roll has happened and the end effector is now in this position where the linearization is somewhat antagonistic towards making progress towards the goal, because it's now in between the object and the goal itself, and the linearization looks like this. So the only way at this point that it could potentially get the object towards the goal is by applying some sort of negative pulling force, which we can't really do. How did C3 get rid of it and actually make those motions happen? Well, it incorporated this time-based gating mechanism where it has a roll phase in which it makes hybrid decisions on making and breaking contact with the object. But those decisions are restricted to the roll phase, which is a timing-based heuristic. And then once it's rolled and it's reached a point where it's stuck and can't make any progress, it doesn't actually make any, it doesn't realize that it's doing that, just that the timing-based gate is able to get it out of this stuck state and move it back into, or reposition it back into where it could be. This is a heuristic-based, system-specific repositioning scheme to get the controller get unstuck from these bad conditions. And the aim of this work is to replace this heuristic-based, system-specific repositioning scheme with a sampling-based, geometry-agnostic repositioning scheme. Why do we think that we want something like this? Well, let's say instead of trying to manipulate that ball, we were trying to manipulate an object that looks something like this, which is this toy jack that we have here. We have the spherical end effector and we have the goal position. And this object right here is a very non-convex object. And so the same heuristics that we had for that ball wouldn't work for something like this. So here's the proposed controller architecture. Let me just walk you through this diagram right here. So we have the Franca simulation. We get the Franca state estimate at about 1000 Hertz. We have the object position tracking also at 1000 Hertz, which obviously works because it's a simulation. The state estimate then goes to this hierarchical contact controller block, which runs at about 15 to 20 Hertz and makes these hybrid decisions. And I'll talk more about it in a bit. And what this controller block does is that it hands over a set of trajectories, it hands over a trajectory and a sequence of actions to a low-level operational space controller that also runs at 1000 Hertz and then hands over the input to the simulation of the robot. Let's dig a little deeper into our hierarchical controller. Before that, why do we think this sampling scheme should work? Essentially, different end effector locations result in different linearizations, and different linearizations result in different costs. And so ideally, the cost should be able to drive our system out of states where it gets unstuck. It's important to note here that our sampling scheme samples in a very low dimensional space of possible end effector locations only. So it's not sampling mode sequences, it's not sampling possible full states, it's only sampling in a small three-dimensional space around the object. Let's take a look at how the algorithm actually works. I know this is a lot on one side, so let me walk you guys through this. Let's look at this little sample generator block. So we see that given the current state of the object and the current mode of the system, here mode refers to whether the controller wants to do C3 or whether it wants to be position. Okay? So given the mode and the current location, current state of the system, the sample generator essentially generates like n different samples, and each of these samples only differ from the current state by the end effector location. Each of these sample states are then handed over to multiple instances of C3 blocks, and C3 solves the optimization problem parallelly for each of these different initializations or possible end effector starting locations. C3 also outputs a cost associated with each of them, possible trajectory of states and inputs. We then hand over all of these costs associated with each of these samples to a process samples and pick the best block. So what does this block do right? Processing samples essentially here means that additional to this base C3 cost that we got from the C3 blocks, we add a travel cost associated with moving from where the end effector currently is to one of these sample locations or to each of these sample locations. And this cost is a 2-node base cost. And then we look at the one that costs the least, and then we hand over that cost and that sample to a spline generator. What the spline generator does is it essentially generates a collision-free curve from where the end effector currently is to the best possible location that it could possibly relocate to at this point. And then this cost is handed over along with a repositioning plan to another add a cost and switching modes, another block that sort of adds a cost on switching modes and picks which trajectory to follow. So what that really means is that with this block, which has information about what the C3 cost currently is from where we currently are, and has information about the best possible alternative plan that we have. And it adds a cost on the current end effector location, and then decides whether whether it can still make progress from where it currently is, or whether it should switch to a more advantageous location. And so, and as an output of this block, we have the next mode that the controller is going to be in, which is either C3 or reposition. Let's look at this in action. So we see right here that at all points in time, we have these yellow spheres that are running around the object are possible samples of end effector location. And based on this information, the controller could either change or could either be in C3 mode, where you see in the visual that the end effector turns pink when it's in the C3 mode, or it could end up in the repositioning mode. And here you see that the it's tracking a repositioning spline to get to the best sample location. And in all the further visuals, you'll see that the C3 mode is always in the end effector is pink in the C3 mode and the end effector is black in the repositioning. Let's take a look at some results. Here, let me just wait for it to start. So we have the object starting at this location. We see that it's repositioning to a better spot now. It does C3 again, and then it very comfortably gets the object to the exact. Just making it very clear here that we're not doing orientation tracking here, we're only doing position tracking, and so it's trying to get the object to that goal. Another example of with a different goal location. So every time the end effector turns pink, it's doing C3, and every time it's black, it's repositioning to a better spot. Here's another example of some results. So we see that the object is like very close to the goal, and now the end effector is trying really hard with these very slow, subtle motions to try and get it closer. Every time it turns black, iterating, it is doing repositioning, and every time it's pink, it's doing C3. And this right here is actually my favorite experiment. So you see here that the goal clearly has a higher C as compared to the resting center of mass of the object. And the controller is able to make decisions on first getting the object to the XY goal. And then in order to get it closer to the Z goal, it actually balances the object on two prongs and then just holds it there, which I think is really cool. So in conclusion, we see that our sampling-based approach actually approximates this global optimal control problem for contact-rich manipulation using local feedback. And so essentially, it's able to make these decisions on two different levels. One is it's able to make this sort of discrete decision on which side to approach the object from. And then it makes these local decisions using this locally optimal controller and make and break contact from these good starting. Some future work that we have in mind is to get hardware experiments and potentially improve sampling strategies. This could mean, for example, the system that we're looking at here, it's a quasi-static system. That is, it doesn't if the object isn't in contact with the end effector, there's no motion. And so potentially, if we could leverage information about previous samples and then further drive better sampling in the next iterations. That's all. Thank you very much.
I'm just curious how you factor contact the environment into.
Well, so in these videos, we're not actually factoring contact between the end effector and the ground. That's a state constraint that we put in the optimization. However, it does throughout reason about ground contacts with the actual object. So you see that it's actually leveraging the contact between the object and the ground to make those rolling motions and sliding motions. And yeah, so it's actually taking ground contact into account, just not between the end effector and the ground, but between the object and the ground. Is that clear?
Yeah. was just wondering how you would change the environment. How?
Well, we could add contacts into the problem. Like, for example, if I were to like add a wall into the problem, then I could like have the controller reason about additional contacts between the object and the wall itself. So maybe I can be a little bit clearer. Right now, this object that we have is modeled as like 3 capsules that are sort of rigidly attached perpendicular to each other, mutually perpendicular to each other. And so the contacts that the whole controller is reasoning about is end effector, capsule 1, end effector, capsule 2, end effector, capsule 3, and then capsule 1 ground, capsule 2 ground, capsule 3. And so essentially it's reasoning about 7 possible, 6.
So I was actually thinking about how, as a human, I would be able to take just my fingertip and manipulate a jack toy along the ground. And it seems, at least it seems to me, that it would be pretty difficult because there would be like a lot of slipping and like rotation induced on the jack that I don't want. So have you tried varying the frictional, like the friction coefficients, and seeing how, like whether it becomes harder or easier?
Yeah, I mean that's actually a good point. So if we were to reduce the friction on the system, then it would probably pick like sliding motions very easily. Versus if the friction is like higher, then it's actually able to roll across the ground.
Yeah, how robust would this technique be with respect to the noise in your state estimation? So like your object S.
So as of now, since this is all done in simulation, we have a perfect state estimate, and we haven't factored in noise in the system yet. But that would be a part of hardware experiments. So right now we haven't induced robustness in terms of state estimate.
Any other questions? How critical is it that you were able to, you were saying how you're getting information if the object is in 1,000 hertz, right? How critical is that in ensuring that?
Well, in the case of a system like this, probably not very much. We can do with much lower rates because, like I said, it's a quasi-static system. And so if we're not making contact with it, it doesn't. But in the case of, say, like a ball rolling, if we don't have constant information about where the ball is, I mean, I'm sure we don't need 1,000 hertz. I don't remember what C3 does it with, but we would probably need a higher information rate.
Any other questions? Thinker speaker?